Okay, so for this integral, I would definitely call it a Brum moment. If I were to call anything a Brum moment, this would be the definition. Okay, so when we look at this integral, right, we have a rational expression, a polynomial over a polynomial, and it doesn't look super intimidating, but we're not going to be able to use, for example, a u substitution, because you might think like, because this is x to the 5, this is x to the 4th, maybe we can use a u sub because the derivative of x to the 5th is degree 4, right? So if we call the top x to the 5th plus 2x minus 3, if we said that was u, right, du would be 5x to the 4th plus 2 dx. And even though this is x to the 4th, this is on the bottom of our fraction, and we want the dx to be on the top. Not to mention we have this extra plus 2 here, but we want plus x cubed. So u substitution is just simply like not going to work in this case. And typically when we see two polynomials or two polynomial expressions being divided by each other, right, a rational expression, lots of the times we're going to be able to use partial fraction decomposition. And the only time we can do that is when the power, like the degree of the expression on the bottom, is greater than the degree of the expression on the top. And that's not the case here, right? Because in the end, what we want is we want a constant over some linear term like x minus 1, for example, plus a constant. We can call them a and b over something like x plus 2. So, and we can have multiple, right? We can keep going. But the main idea is that we want to have a constant on the top and a linear factor on the bottom. And we're going to add a bunch of those together, and hopefully we can make an equivalent integrand here. Okay, and notice that the degree of a constant is 0, the degree of a linear term, like x minus 1, is just 1. So the degree of the numerator of fractions has to be less than the degree of the denominators if we want to use partial fraction decomposition. So unfortunately, we can't just jump into this problem and say, okay, we're going to do partial fraction decomposition, because we can't, right? This x to the 5th, its degree is 5, x to the 4th degree is 4. Well, 5 is greater than 4, and if the 5's on top, we can't do it. So let's just divide this using long division with polynomials and see what we get. Okay, so I have a video on this, but I'll kind of walk through my steps here. So we have x to the 5 plus 2x minus 3. We're taking that and we're dividing it by x to the 4th plus x to the 3. So we don't know exactly what this is going to be, and it's probably not going to divide into it perfectly, right? That's just my guess, but what we're going to get is we're going to get a quotient up here, right? Maybe like x plus or minus something. And then at the bottom here, once we're finished, we're going to get the remainder. And the remainder is really what we're focused on. So I'll stop talking, we can do it here. So what we have to think about is we have x to the 5th, x to the 4th. Those are the first terms of each kind of expression. We have to think, how many times does x to the 4th, this first term, go into x to the 5th, this first term? And it goes in x times, right? Because x times x to the 4th is x to the 5th. So if we take this x and now multiply it into these two numbers, we're going to subtract that from everything on the inside, right? Just like we did in long division with no variables. So x times x is x to the 5th. See how these x to the 5ths are going to cancel now. And x times x to the 3rd is x to the 4th. So when we subtract that, right, the x to the 5ths are going to cancel, and we're going to get negative x to the 4th. Okay, and one thing we can't forget is to bring down these numbers here, because they're still there, right? But we didn't have any linear or constant terms to add or subtract when we multiplied by x. So we just kind of have to bring them for the ride. Okay, now we have to think, how many times does x to the 4th fit into negative x to the 4th? Well, it fits in negative 1 times, right? Because negative 1 times x to the 4th is negative x to the 4th. So again, we take this negative 1 now, the new number, multiply it into x to the 4th plus x to the 3rd, and we subtract that from everything left on the inside. So it'll be negative of negative x to the 4th plus, well, negative 1 times x to the 3rd is negative x cubed, right? And that's it, right? There's just two terms. So these x to the 4ths are going to cancel, and we're going to get a negative of negative x cubed. That's going to be positive x cubed, right? Plus 2x minus 3. So this is our remainder. We can't do any more because x to the 4th doesn't fit into x to the 3rd. It's too big. So whenever that happens, we just stop here and say the quotient is x minus 1, and the remainder is x to the third plus 2x minus 3. So I'm just going to take this and kind of shift it down so I can show you what I mean. Okay, I'm going to shift everything down here. So an equivalent way to write this integral is the integral, right, of the quotient. So when we actually take these numbers and divide them, what we get in full is x minus 1. So I'm just going to write that. X minus 1. Okay. And then, right, we're left with this. So this is our remainder. Whatever we have our remainder, we take that remainder and we divide it by what we're dividing the whole thing by. So the whole quotient is x minus 1, but we have to add this remainder over the divisor. So that's just kind of a property of long division. So we can call this its own integral, right? And then we're going to be adding the integral of the remainder over the divisor. So the remainder is x cubed plus 2x minus 3. And then we're going to be dividing that by x to the fourth plus x to the third. Okay, so this part, the x minus 1, the integral of x minus 1 dx, this isn't our problem because we can integrate that easily using the power rule. This part right here is our problem because we're still faced with the same issue as when we started the question. We have two kind of higher degree polynomials being divided by each other. But you might think like, well, what was the point of using that long division if we didn't get anywhere? Well, actually we did, because remember we started with x to the fifth in the numerator and we whittled it down to x to the third. So that's great because now we can use partial fraction decomposition to actually kind of break this thing apart. And it's going to be a long process, I'm not going to lie. It's going to be kind of algebra intense, but the calculus for the most part is done for the next little while. So we're not worried about this integral. Let's just focus on this part right here, the last integral. Okay, so let's look at just the inside, right? And let's try and break that up. So what we have right now is we have x to the third, let me just write it here, plus 2x minus 3 over x to the fourth plus x to the third. Okay, so that was our remainder over our divisor. Now, how can we take something like this, right, and break it up into multiple fractions that are adding or subtracting? Because the main problem right now is that it's all one fraction, and we don't have a rule when we're integrating where it's going to accommodate everything, right? Because x to the fourth, x to the third, maybe u sub there, but then we're faced with these two x's, these constants, these x cubes. So we're going to have to break these up and get them as a sum or difference, and then we can integrate each of those individually. It's going to be a lot easier. Okay, so what we want to do is we want to think, well, first of all, let's factor out x cubed, or let's factor, yeah, x cubed. So it'll be x cubed times x plus 1 on the bottom. That'd be my first suggestion. And then whenever we're doing partial fraction decomposition, we can break this up and say that this thing on the left is equal to some constant a being divided by the lowest possible degree of variable here that's a factor of this denominator. So in this case, that's x. Because x is a variable factor of x cubed times x plus 1, and it's the smallest degree, we can say we can add another constant b over kind of the next order up from x, which is x squared. Notice x squared is still a factor of x cubed times x plus 1. We're adding c over the next factor up is x cubed, right? X cubed is in fact still a factor. And then x to the fourth is not a factor, right? The only factor left is x plus 1. So we're going to go plus d over x plus 1. So that's how you'd set it up, is you'd say, okay, we need to find all four of these constants, right? And this is essentially going to be our answer. It's going to be a constant over x plus a constant over x squared plus a constant over x cubed plus a constant over x plus 1, because all four of these denominators are factors of our original denominator. Okay, so the next thing we have to do is we have to try and get rid of the fraction on the left. So you might remember from my rational expressions video, when we want to do this is if we have a fraction we want to get rid of the bottom, we multiply everything by the denominator. So when we multiply both sides by x cubed times x plus 1, we just get what was on the top. So x cubed plus 2x minus 3. Okay, that's all good. Now what we have on the right, we have to multiply each term by x cubed times x plus 1. So the first one, I'll write it a bit bigger because I won't have room, is going to be a times x cubed times x plus 1, because we're multiplying the entire thing by x cubed x plus 1, and then over x, right? X was already there. So notice how this x cubed and this x, they have common factors of x. We can divide the top and bottom by x, and we just get x cubed on the or x squared on the outside now, right? Because x cubed over x is just x squared. So we're going to get a times x squared times x plus 1. And I'll have to write this smaller. A x squared times x plus 1. Okay. So notice how it's the exact same thing as the denominator here, except it's just a factor of x smaller, because we're taking this denominator and we're dividing it by x. Okay, let's do the same thing with b squared, right? If we had b over x squared, okay, and we multiply it by the denominator on the top and bottom, right? And you might forget the reason why we can do this is because x cubed times x plus 1 over itself is just 1. So we're not changing the value of anything, we're just manipulating the equation. Okay, so this x cubed and x squared, they're going to have common factors of x squared. So two of them cross out on the top and the bottom, leaving us with, well, we actually don't have to do it on the top and bottom, right? Because it's an equation we multiply by x cubed times x plus 1 on both sides. So actually we can just multiply it by this, and we'll get b times whatever's left over, which is x times x plus 1. So plus bx times x plus 1. And you kind of get the idea, right? With the c over x cubed, we're going to multiply that by x cubed times x plus 1. The x cubes are going to cancel, and we'll just get cx plus 1. Okay, and then the last term, d over x plus 1 times x cubed times x plus 1. Well, the x plus 1 factors are going to cancel out now, which is nice, right? And we're going to get dx cubed. Okay, so now it's a little nicer because we don't have a fraction anymore. We just have a polynomial equation, and we're trying to simplify. So the next thing we have to do is, what we're really trying to figure out is the a, b, c, and d, right? A, b, c, and d. These are just constants. And the tricky thing that we can do is we can just plug in random values for x and see what we get out. So we have to be smart with it. We have to think of what values of x will eliminate as many of these terms as possible. So we kind of whittle down what we're going to work with. So the first thing I suggest is calling x equal to 0. Because if I just say let x equal 0 here, let x equal 0, right? If x was 0, on the left we'll get 0 plus 0 minus 3, so that's just negative 3. And on the right we get a, whatever that is, times 0 times a number, so that's going to be gone. We're going to get b times 0, which is gone. C times 0 plus 1, which is c, so we get c. Right? And then d times 0 cubed, which is just 0. So just like that, by saying x equals 0, we know that c is going to be negative 3. We already figured out what c was. So I'm going to write this a little smaller here. C equals negative 3. So we just figured that out. We already got one of them. Okay? Now we also have to be smart with what we pick next. We have to think of what x value will eliminate as many of these terms on the right as possible. Well, notice how all of them except one have a factor of x plus 1. So I'll say, all right, let x equal 0 over here. If we also said x was negative 1, right, then this term would be gone, this term would be gone, this term would be gone, and we'd be left with the last one. And the reason for that is because the first term will be a times negative 1 squared times x, or sorry, x is negative 1, so it'll be times negative 1 plus 1. Well, negative 1 squared is 1, so it'll be a times negative 1 plus 1 is 0, so it's going to be a times 0. So any term with a factor of x plus 1 in it will disappear, essentially. So what we're going to get is, on the left side, we're going to get negative 1 cubed plus 2 times negative 1 minus 3 equals, all these three will go away because they have a factor of x plus 1, and we're going to be left with d times negative 1 cubed, because d doesn't have that factor of x plus 1. So negative 1 cubed is negative 1, plus 2 times negative 1, so minus 2, and then minus 3 from that is negative 3 minus 3, which is negative 6, is going to equal, well, negative 1 cubed is negative 1, so negative 1 times d, so negative d. That means that d therefore must equal 6 if we divide both sides by negative 1. Okay, so we figured out c and we figured out d. Now comes a part that's kind of tricky to think about, because by putting in x was 0 and x was negative 1, we simplified 3 of the 4 terms. They just disappeared completely. But now we don't have really a trick to do that, because we already used 0 and negative 1. None of them, like, it's not going to happen again. Like, they all don't have a factor of like x minus 2 or something except 1. We've already used that trick. So what we have to do now is pick the next kind of smallest value for x and make a system of equations. So now let's just say let x equals 2. Okay, that's probably the next one I'd pick. So actually let's do x equals 1. Let x equals 1, that's the next one, because we only did negative 1, we didn't do positive. So if x equals, pardon me, if x was 1, let's plug in 1 for x wherever we see x. So it's going to be 1 cubed plus 2 times 1 minus 3 would be equal to, so it'll be, I'll just simplify it a bit just for the sake of room. That's going to be a times 1 squared times 1 plus 1, so a times 2, which is 2a. Right, and we're going to get the same thing here. So it's going to be plus 2b. Okay, and we already know what c and d are. So if this is c times x plus 1, this will be, remember c was negative 3 times 1 plus 1. So that's negative 3 times 2, so that's negative 6. Okay. So it's negative 6, and then what we're going to get now is, if d is 6 and x is 1, this will be 6 times 1 cubed. So we're going to be adding 6, right? This is just going to be 0. So it'll be negative 6 plus 6, right? That's 0. So if this equals 2a plus 2b, well, 1 cubed is 1, plus 2 times 1 is 2, minus 3 is 3 minus 3, which is 0. So 0 equals 2a plus 2b. If we divide both sides by 2 and move one of the a or b's over, we can just get a is therefore equal to negative b. So it's going to be nice because whenever we find a, we can just take the negative of that and we're going to get b. Or vice versa, if we find b, we'll just take the negative of that and get a. Okay, so this is one of our system of equations. Or it's one equation for our system. But in order to solve for 2 variables in a system, we need 2 equations for our system. So we plugged in x was equal to 1. What's the next smallest one we haven't used yet? We did x equals 0, x was negative 1, x was positive 1. Right, let's do x equals 2, because positive small numbers are good. So let x equal 2. Okay, so we're going to do the same thing. We're just going to plug in 2 where we see x now. So this left side, I'll just do it kind of in my head here. 2 cubed is 8, plus 2 times 2 is 8 plus 4. So 8 plus 4 is 12, and then minus 3 is going to be 9. So this left side here, when x is 2, is going to be 9. Okay, so now we know that 9, that's going to be equal to, let's see here, a times x squared. Remember, x is 2, so it'll be a times 4. So 4a times x plus 1. So it'll be 4a times 3, So that'll be 12a. So 9 equals 12a. Remember, we're still using x equals 2. So b times 2, which is 2b, times 2 plus 1. I'm looking at this part right here. So 2b times 3, right, because x is 2. So that'll be 6b. So it's going to be 9 equals 12a plus 6b. This is looking nice because they're all factors of 3. Hopefully we can divide. And then after that, we're just plugging in 2 for these last two as well. So remember, c was equal to negative 3. So this will be negative 3 times 2 plus 1. So negative 3 times positive 3, which is going to be negative 9. So I'll write minus 9. And then d was 6 and x is 2, so that's 6. That's going to be 6 times 2 cubed. So that'll be 6 times 8, which is 48. Okay, so that'll be negative 9 plus 48. Remember, negative 9 plus 48 is 39. So plus 39. So now we're going to get, we can divide every number by, well, let's actually move the 39 with the 9. So we subtract 39 on both sides. We get negative 30. That's going to be equal to 12a plus 6b. Okay, notice how all these are divisible by 6. So if we divide everything by 6, we get negative 5 equals 2a plus b. Okay, we're just dividing everything by 6. And remember that b, right, that was also equal to negative a. They were just opposite from each other. So instead of saying plus b, we can say negative 5 equals 2a plus negative a. Because that's really what b is. And adding a negative, that's just like subtracting a positive. So 2a minus a, that's just going to be a. So just like that, we figured out a is negative 5. And remember how I said before, if we figured out a, we can immediately know what b is because it's just the opposite of that. So therefore, b is equal to positive 5 because they're just negatives of each other. So now we know a, b, c, and d. Okay, so that's awesome. We're going to get, I'm just going to write it here. A equals negative 5. B equals 5. C equals negative 3, right? And then D was 6. Okay, so remember our original formatting here. A over x squared plus b, or sorry, a over x plus b over x squared plus c over x cubed, and then plus d over x plus 1. So I'll just write that here. A over x plus b over x squared plus c over x cubed. And we had this plus d over x plus 1. Okay. So a was negative 5. So let's go negative 5 over x plus b was positive 5. So plus 5 over x squared plus c was negative 3. So we're going to go minus minus 3 over x cubed. And then d was positive 6, so plus 6 over x plus 1. So if you try to simplify this and make it one fraction, right, you're going to find that it's the same as the fraction we started with, which is this part right here. So we essentially just totally decomposed this fraction using systems of equations, right, algebra, manipulation, that kind of thing. And notice how this part here wasn't our entire integral. It was just the part of the integral we had before. So we still had this integral of x minus 1 dx. Okay, so we still have to add that. We have the integral of x minus 1, dx. So that's what we had before. And now we're taking the integral of all of this, right? So since these are all adding and subtracting, it's going to be nice because we're going to be able to like take the integral of this one, and then the integral of this one, the integral of this one. That's a property of integrals, right? which is always nice to work with. So we're going to have the integral of x minus 1 dx, and then remember we're subtracting the integral of 5 over x dx, and we're just taking the integral of each individual component of the sum. So it's going to be plus, right, the integral of 5 over x squared dx, and then minus the integral of 3 over x cubed dx, and then plus the integral of 6 over x plus 1 dx. So this is a totally equivalent way to write the original integral, right? This is the integral of x minus 1, which we found up above here, right? That's what we had before, and then we said we take that and we add the integral of all this stuff. Well, using partial fraction decomposition, we just split this up. We blew it up into 4 different fractions. And since those fractions were either adding or subtracting together, we can just take the integral of each part of the sum or difference and add those together. We can use our property of integrals. So let me just simplify this a bit more. This is the integral of x minus 1 dx. And notice how this 5 is multiplying into 1 over x. So it's going to be minus 5 times the integral of 1 over x dx. And then it'll be plus 5, the integral of 1 over x squared dx, minus 3 times the integral of 1 over x cubed dx, and then plus 6 times the integral of 1 over x plus 1 dx. Okay, so now we have that. Now it's just a matter of evaluating each of these integrals individually. So it's going to be, the integral of x minus 1 dx is 1 over 2x squared minus x, right, using the power rule. And now we have a 1 over x. Well, the integral of 1 over x, remember, is just the natural log of x, because if we try to use the power rule for this, right, 1 over x is x to the negative 1. Well, if we add 1 to the exponent, we'll get x to the power of 0 over 0. Using the power rule, that's undefined, so we can't do that. And we just know it's the natural log. So it's going to be minus 5 times the natural log of x. Okay, and then we have plus 5 times, well, what's the integral of 1 over x squared? This is the integral of x to the negative 2, right, dx. That's an equivalent way to write it. So to simplify this, we can use the power rule. So remember, we take the power, negative 2, we add 1. So it's going to be x to the negative 1, and then divide by that new power. So it's going to be negative 1 over x. Okay, so it'll be 5 times negative 1 over x, or we can just say minus 5 over x. Okay, that's totally acceptable, right? And now we have that figured out. Okay, let's just keep track of what we've done here. So we've done these first 3. Now we're on 2 minus 3 times the integral of 1 over x cubed dx. Well, we use the same idea, right? X cubed in the denominator, that's the same as x to the negative 3. The integral of this with respect to x is just the power being raised by 1, so x to the negative 2, divided by that new negative 2. So it's going to be negative 1 over 2x squared. And then remember, that's being multiplied into the 3 that's already on the outside. So it's going to be, right, negative 3 times negative 1 over 2x squared. So negative times a negative, that's a positive 3 over 2x squared. Okay, and then we have plus 6, or the integral of 6 over x plus 1 dx. Well, x plus 1 is a linear term, or a linear expression, and anytime we have a number, a constant, being divided by a linear term, we're taking the integral of that. It's going to be that constant, right, 6 times the natural log of the absolute value of that linear term. So 6 times the natural log of x plus 1, and then we need that plus c there. And the reason we didn't need to add a plus c for all of these 5 individual components is because that way we would be saying a constant plus a constant plus a constant, And whatever the constants were in the end, it's still going to be a constant. So we only need to add it once. Okay, instead of writing plus c after each one. So even though they all are indefinite integrals and need a plus c, the plus c at the end is just going to combine. We only need one. Okay, so this is technically our answer. Now, if we wanted to make it harder on ourselves and think that we weren't quite done, we wanted to keep going, we could take all of these polynomial and rational expressions and kind of combine them into one fraction. So let's move the minus 5 ln x plus 6 ln absolute value of x plus 1, right? And we have the plus c. Okay, what if we wanted to do the 1 over 2x squared minus x minus 5 over x plus 3 over 2x squared? Well, if we wanted to combine those, we would need a common denominator. So right now, the 1/2 x squared, that's x squared over 2, right? If we wanted to make this 2x squared, we need to multiply the top and bottom by x squared over, by x squared. So this would be x to the 4th over 2x squared. Right, notice how these are the same thing, except the denominator is just different. Now it's 2x squared instead of just 2. So now that matches this 2x squared and this 2x squared, they can add with each other. But we want that to be the case for this 5 over x, right, and this negative x. So negative x, right, that's negative x over 1 right now. So we have to multiply the top and bottom by all of 2x squared. So it's going to be minus 2x cubed on the top, because 2x squared times x is 2x cubed over 2x squared. Okay, that's what we got. And then this negative 5 over x, there's already an x in the bottom. We have to multiply it by 2x to make it 2x squared. So it's going to be minus 5 times 2x, which is just minus 10x over 2x squared. And then we have plus, well, the 3 over 2x squared already has a common denominator there. That's what we were basing it off of. Okay, so now since all these denominators are the same, we can go x to the 4th minus 2x cubed minus 10x plus 3. And all of that is being divided by 2x squared. So that's an equivalent way to write what we have above. And then, of course, we have minus 5 ln, I'm going to write the absolute values here, plus 6 ln x plus 1 plus c. So this is the final answer, right? It took us a long time to get there, but we got there. You can put into Wolfram alpha or whatever, and you're going to get the same answer. And don't forget this plus c, because if you do this on a test, you do all this work, don't write the plus c, you're going to get marks off. It's free marks to write the plus c. Okay? So I hope this made sense. And yeah, this is probably like the hardest type of question you can possibly have with integration by partial fraction decomposition. So we kind of worked our way up, but we got there, and I hope you enjoyed.